in the last class, we so what we will do is that we will solve few questions based on that. The questions are very limited from this area, but once you are going through the lecture now, then questions will be very easier for you to understand, and you can solve it within seconds just by looking after the statements of the given question. So the questions, it might look like it has a lot of data, but the questions can always be sorted just a few by looking at option. Okay, so now, so let us first solve few questions. Okay, so it says that the mathematical expression of NTU in a heat exchanger, so it has denoted their meanings also, like U, it has says that it is overall heat transfer coefficient, and it has says that C is heat capacity, E is the effectiveness, E is the area of heat exchanger. So if we can recall, then we learned that NTU, number of transverse unit, was U multiplied by area of the heat exchanger, and C minimum, right? And heat capacity they have denoted C. So like C, we have in this manner, and C is also and so where is this option? We can see in A option, right? That UA upon C minimum. Correct option is option A. Okay. Let us go to the next. It says that when is arithmetic mean temperature difference used instead of LMTD in heat? So we can recall that what happened, that we studied two special cases of LMTD, and then we learned that when we were working with the counter flow, and in the specific heat, not specific, the product of specific heat and the mass, the product of a specific heat for both the hot and cold fluids were the same, then we decided, then we learned that the arithmetic mean itself is the logarithmic mean temperature difference. So which option will say this one? Temperature profiles of two fluids. So instead of that, it has given option in terms of what? Temperature profile. So we also learned that temperature was remaining constant, right? Like delta Ti was delta Te. So the temperature profiles, we decided that the everywhere temperature difference was constant. If this is delta Ti and this is delta Te, then we decided that everywhere the profiles were constant. Okay, so once this is constant, then what is that? The difference between any 2 points at everywhere is the same only. Okay, so that is why it will be what? It will be nothing but the linear profile. Okay, so what I can see is that this is straight, right? So where this option, like it says that straight lines, so can we see that when temperature profiles of two fluids of heat exchanger are straight? Okay, then next question. It says that for evaporators and condensers, for the given conditions, the LMTD for parallel flow is. Then this is one of the special case again. It says that for evaporators and condensers, for the given conditions, it asks you that LMTD for parallel flow is. Then we learned that this was LMTD who was equal to equal for both of the flows, right? Like for parallel and counter flow, it was same. So which option says that equal to the counter flow will be the correct option? So the option A is the correct one. Okay, let us move to the next. Then it says that what is the question? It says that consider following facts about falling factor. So let us read them one by one. Is a dimensionless quantity? No. We remember, we learned that, can you recall that the unit of falling factor was something? It was just the reverse of h, like the f was unit of, like if I talk about just unit, then it was reverse of h, right? reverse of H. In that manner, I can say that F is not dimensionless quantity. So one option is wrong. So let us go to now the given option. So if option number 1 is wrong, then I can cut option A is not the correct one. Option B says one option and option E also says. And then we can see that two of the options, one is 2 and 3. It says that 2 and 3 is correct, and we can see 2 and 3. So 2 and 3 is common, then I can like see this. Sometimes we can utilize this kind of analogy into solving the what objective questions, so where multiple statements are given. So without even reading the second and third statement, I can say that looking after the options, like either option C is correct, either option D is correct, but I can see that both of the options are containing second and third statement. That means second and third are automatically true. Then I will only read the fourth one, and then I will just okay. This is 1 minus to the power minus of 1 plus c into NTU divided by it was 1 plus c. Okay. And what was for counter flow? E for counter flow, this was 1 minus e to the power minus of 1 minus c into NTU divided by it was 1 minus to the power c was already here minus 1 minus c into NTU. This was this, right? So now it says that that when this case is valid, like when we are going to have this condition, and then when you put c is equal to 0, when you put c is equal to 0, can you see that this is 1 minus e to the power minus NTU, and here also this is 1 minus e to the power minus NTU. So when c is equal to 0, and c itself was the ratio of 1 m dot cp is small upon big. Okay, m dot cp of big. And again, what do we appreciate here is that if m dot cp is very big, then this c value can turn into what, 0. Then this big was coming for which condition, for boiler and condenser, and for both parallel and counter flow. So what is the correct option here now? Option C. Like we have seen just now, we have seen that even though it was parallel or counter, doesn't matter. If the value is 0, then this reduces into this one, and then this is valid for both boiler and condenser. Why boiler and condenser? Because in both of the cases your fluid is changing its phase, and whenever there is phase change, there is very huge heat capacity associated. Okay. It says that the designer chooses a value of what? Flow rates and specific heats in such a manner that the heat capacities of the two fluids are equal. So what it has already mentioned you that heat capacities are equal, then can I write down that they are trying to mention us this way? Heat capacities of fluids are equal, then it says that a hot fluid enters the counter flow heat exchanger at 100 degrees Celsius and leaves at 60 degrees Celsius. Okay, then it says that a cold fluid enters the heat exchanger at 40 degrees Celsius. Then it says that the mean temperature difference between the two fluids is, what is the mean temperature difference they are willing to ask us, and let's highlight the keywords. So it says this is for counter flow, and it has also mentioned one of the condition is that heat capacities are equal. Then whenever heat capacities are equal, then what is, whenever your heat capacities are equal, then whenever heat capacities are equal, then either of these delta T or delta TE are nothing but here total operators Celsius Celsius. So, so I told you that either of the delta TE or I or delta TE. But if you are, let us say that sometimes you are confused that which is I or which is E, so you can name it as delta T1 or delta T2 even. Okay, since I told you delta T and things in terms of what, delta Ti and E, that is why I am using that notation only again and again. But we can also name it as delta T1, delta T2. So what I can see is that any one of these two were the LMTD, and now I am able to find out any one of this one. Then why I need to find out the other temperatures, I can directly say that this is nothing but the 20 degrees Celsius. So see, you know, how big question, so many of datas, but just by drawing just one figure we were able to solve. So questions in these areas are simple, but you need to take care that how they are correlated. Okay, now next question, it says that in a heat exchanger, the oil is cooled from 135 degrees Celsius to 15 degrees Celsius with the water. Okay, and the oil is being cooled with the water. If the water inlet temperature is 5 degrees Celsius and oil and water has the same mass flow rate, Cp oil 1.4 joule per gram and Cp water 4.16 joule per gram, then it says that the water outlet temperature is, water outlet temperature they are willing to find out. So let me help you how to find this one. So what are the things given to us? Let us try to recall them. Okay, so can you see one thing, that it is Cp oil, what is this one? So what do you know about m dot C? Like here what do you need to do is that m dot H Cph into what, delta T, or not delta T, like I can write Th I this is equal to dot PE into TC. TC. Yeah, we need to what is TC to the temperature. So this the same rate. The mass state. So can I take out these two values? Yeah. So now what I would do is that CPH. What is CPH? Oil is cooled. That means this is the hotter one. So what is H is 1.04 into THI. What is the hot fluid inlet is 135 and it has been cooled till home 15 degrees Celsius. So hot fluid outlet is 15 and this is equal to CPC. What is your CP of water? This is given as 4.1. Is unknown here and what is TCI? TCI is given is that if water temperature is 5 degrees, right? So this is minus 5. Then you see that 1.4, this is 4.1, this is exactly 4 times. Is 120. This is 4 PC 4 PCE minus 20. So I see 4 40. C is 140. This so the CE is fluid temperature is probable nature of form appearing in the species. So now let us understand the emissions. Okay. From radiation, so we get radiations and for radiation thermal radiation. So one thing or magnetic spectrum, right? Like there is one electromagnetic spectrum, but I am only willing to what analyze those electromagnetic waves whose wavelength are falling in which range from 0.1 micron to whom 100 microns. Okay, so this is the range where your thermal radiation lies. Okay, now so we before we go to understand more about radiation, let us understand few terminologies. So radiation we have talked about that this is the mode of heat transfer which happens through with the help of what electromagnetic waves, and second most important those waves who are falling in this range, and then we have known the Stephen Boltzmann's law also. Then what does it mean? That your electromagnetic waves are very much function of temperatures. Okay, so your this is the higher wavelength, right? So higher wavelengths means what? Lower temperature. Lower temperature means what? Lower temperature means long wavelength. Okay, and high here what do we have? Short wavelengths. So short wavelengths, and here what do we have? Higher temperature, right? So higher temperature and then we have short wavelengths. Okay, so this is your electromagnetic spectrum. Okay, now basic definitions. First thing is total hemispherical emissive power. What is that? Total hemispherical total hemispherical emissive power. What is this total hemispherical emissive power? See, it is defined as the radiation energy emitted from the surface of a body, where emitted from the surface, but we should like keep this concept in mind that we are talking about what? Emitted from the surface. Okay, so emitted from the surface, how how per unit area in all the possible what? Per unit area emitted from the surface, per unit area in all the hemispherical direction, in all the hemispherical directions, in all the hemispherical directions. Okay, directions, and then you integrate it what? Through the wavelengths through which it is in what? Emitting its power. So integrated overall wavelength over what? All the wavelengths, over all the wavelengths. Okay, so and per unit area, and this is per unit time also, per unit area, per unit time. Then only per unit time we should always know, then only I can find the rate, right? So now what is my total hemispherical power? E, denoted by E, this is equal to whom? Joule per joule, like this is the energy, joule emitted by what? Per unit area, per unit time. So can I write down per unit area, per unit time? So joule per second is nothing but watts. So watts per meter square. Okay. So another important thing is, and one thing we should always understand, that whenever your temperature increases, your emissivity will also increase. What emissivity? Not emissivity, I am telling you total hemispherical power. So when your temperature increases, your emissive power also increases. Okay, the next thing is total emissivity. What is that? Total emissivity. So what is this? See, you have emissivity means what? We have one black body which has been idealized as the, like this is the ideal surface who can emit the maximum what? Maximum or what I can say, that it will be emitting maximum power from its surface, right? So this is black body. Then every body which we see in the nature is not the black body. Then how to find out the emissive power for non-black body? So this is the this is the emissivity which will be helping us to do this job. Then what I am trying to say is that what is total emissivity? It is the ratio of, what is total emissivity? It is the ratio of, it is the ratio of what? Ratio of emissivity, what you have to the black body emissive power. So what is now emissivity defined as? Emissivity, here we are denoting it by epsilon. This is the ratio of E upon EB. So E is my emissive power of any body, and EB is the emissive power for the black body. Okay, but provided we are talking about what? The same temperature. So E is the emissive power of E upon EB, and talking about that at the same temperature. What does it mean by same temperature? Like you are calculating E E and EB both at the same temperature, and then when you take the ratio of these two, then it becomes what? Total emissivity. Fine. Let us go to the next. Then for anybody, what will happen is that my emissivity will always be less than or equal to 1. Yes or no? And for EB, take care of these also. Okay, next. Now let us define what is black body. What is black body? So black body is defined as it is the body which absorbs all the thermal radiation incident upon it. Then what is the meaning, physical significance of this? See, whenever there is some radiation falling upon, then that body has the nature that it can what? In not absorb all of them, it can reflect someone, it can transmit someone. So black body are those bodies who are those bodies who absorbs all the thermal absorbs all the what absorbs all the thermal radiation in. Fine, no problem. Okay, now, so there is one more fact that a thermally black body will not appear always black. Like we can be misguided that a black body should always look black. And what is that expansion? What is the exception? Exception is snow. So snow is also a black body, but this appears white to our eyes, right? So snow is also, for example, I can write that the snow is a black body. And what is that? Another thing, a tiny cavity. A tiny cavity. A tiny cavity is also nothing but a tiny cavity is in a hollow container. In a hollow container is also an example of nothing but what? Black body. Okay, what happens in the tiny hollow container, right? That all the radiations which are reflecting upon it now, then it will see what happens is that let us say some radiation is falling upon it, then it will and it will reflect someone. So what happens that all the what the radiations which are reflecting from one point will get attracted to the other point, and in that manner I can say that it has absorbed all of the radiations. Okay, now let us go to whom? Monochromatic or spectral emissive power. Monochromatic or we can say spectral emissive power. What is this monochromatic or spectral emissive power? See, now let us say that you have hemispherical emissive power, right? Total hemispherical emissive power. But sometimes what happens is that your body is defined, like your body is working for particular d lambda, right? So what I'm trying to say is that when you have e lambda, like you have e lambda, so E lambda is nothing but your spectral emissive power. So what is this? Is that once you know E lambda, then when you go to find out that what happens between lambda to d lambda, like if this is your lambda and this is your lambda plus d lambda, then I am willing to find out that what happens and what is the emissive power during this d lambda only. So if I know emissivity or not emissivity, the emissive power as the function of lambda, then if I integrate it between the given limits, let us say that I am taking 0 to infinity, and if I integrate it between the given limits, then what I will do is that I will be able to find out what is my monochromatic emissive power. Okay. So let us integrate it E lambda into D lambda, right? Now, so then if we have monochromatic emissive power, then we can have monochromatic emissivity as well. So let us understand monochromatic emissive power, right? Not in emissive power we have seen now, so this is emissivity. So what is monochromatic emissivity? So now your E lambda, like epsilon lambda, will be ratio of whom you have E lambda divided by EB lambda, right? So can I write down now my E lambda is nothing but epsilon lambda into EB lambda, right? So this is the idea of having a spectral or monochromatic emissivity. Then now if you are willing to find out that what is the ratio, then can I write down this one as like this is the ratio of 0 to infinity E lambda to D lambda divided by this is 0 to infinity EB lambda into D lambda, right? Okay, and then you can also write that this is, you can also write this one as this one. So can I write this is nothing but 0 to infinity E lambda into EB lambda into D lambda divided by 0 to infinity EB lambda D lambda, right? So now E lambda is not the function of lambda, right? So this is rather what, constant. So this is one conclusion, like E lambda, can you see that if I take E lambda from here, from out of the integration, then this and this will get cancelled out. So your E lambda is not the function of whom, lambda. So E lambda is rather constant. So can I see one thing now, that the emissivity which we have seen earlier is equal to E lambda, that is equal to the monochromatic emissivity. So one thing which is done here now is that this monochromatic emissivity is not the function of lambda, and this is valid for whom, like we have seen here that when E is equal to E lambda, then this is valid for whom, like this is valid for whom, for those bodies whose whose spectral emissivity is not the function of, or what I can say in general, like let me say here is that whenever I can say that my monochromatic emissivity monochromatic emissivity E lambda is independent of wavelength, independent of wavelength, and when this is independent of wavelength, then I term these bodies as what? Gray bodies. Okay. So for gray bodies, what happens? For gray bodies, monochromatic emissivity E lambda is independent of what? Wavelength. So I can say that my E lambda is assuming certain constant value. Okay. So what happens is that your emissivity depends upon the wavelengths also. Like whenever you are working with non-grace bodies, then what happens is that your emissivity, like how much you are emitting, is your ability to emit is dependent upon your what? Wavelength. But there are certain bodies in nature who are not emitting with respect to their wavelengths, so then those bodies are called gray bodies. So got the idea? There can be general bodies whose emissivity is function of their wavelength, but there are certain bodies for whom their emissivity is not the function of wavelength, then those bodies are called what? Gray bodies. Okay. Now next thing is, we should let us now try to understand, like whenever there will be some radiation energy falling upon a body, then this body has some tendency to do certain things. What are those tendencies? Then this body can absorb something, like let us say, for example, here what I am trying to say is that, let us say that there is a body here, and upon this body there is some incident radiation. Let us say that 100 units of radiation is falling upon you, then this body has tendency that it might absorb 50, and then this body has the tendency that this is transmitting 50 out, like 25 out of this like left 50, and it has the tendency that it is reflecting 25 units. So what are those things? Like you have some incident radiation, then it can reflect some and it can transmit some. Okay. So based on this fact, we have absorptivity, reflectivity and transmissibility. So first thing is absorptivity. So we denote it by alpha. This is absorptivity. So what is this absorptivity? It is the ratio of what you have absorbed. So what you have absorbed, like absorbed radiation divided by whom? Divided by total incident, right? So for example, here what we can see, for example, we can see here is that it has absorbed 50, like 50 is absorbed with this one, and how much was the total incident? Was 100. So what is absorptivity now? 0.5. And then we have second case where we have reflectivity, rho, denoted by rho is reflectivity. Reflectivity denoted by rho. This is the ratio of how much you have reflected, divided by what was the again total incident, right? So what is here reflected amount? 50 units you have reflected, right? So 25 you have reflected, right? So 25 divided by 100, this is now 0.25. And then we have third case where you have transmitted some. So this is denoted by tau, and this is transmissibility. Got the idea? So this is transmissibility. So what is the ratio of this one? That how much you have transmitted divided by again whom, what was the total unit which was falling upon you. So total incident. Then can you see this is again, for example, this is 25 by 100, But this is not the case that every time a body will always, like, it will reflect or transmit. It might happen that it is absorbing all of those, then this is becoming black body. Then it has the tendency that it is reflecting all of them. Then it has tendency that it is not transmitting any one of these. So depending upon the body, these reflectivity, absorptivity and transmissibility can vary, right? So those bodies, like for opaque bodies, those bodies who are not able to transmit any energy, so what I am writing here is that for opaque surface, for opaque surface, for opaque surface which doesn't transmit, which doesn't transmit any energy, which doesn't transmit any energy, then your reflectivity is directly 0. Then can I write down that okay, one more thing before this, that can you see one thing, the fraction of these two, these three in fact, alpha, rho and tau is 1 only. Can you see that the summation of these two, alpha, rho and tau, is 1 only? Every time this will be followed. Why? Because every time you will be having 100 in the denominator, and every time what the sum will say, the total of 100, like incident. So here 50, 25 and 25, so this is 100 only. So then every time this is valid for everybody. But depending upon that, if certain times your reflectivity, transmissibility was 0, then what does it mean? That this is the opaque surface, right, who is not transmitting any surface. This is what? Opaque surface. Then can I write down that alpha plus rho, this will be equal to 1 only. Why? Because this value is directly 0. And for any surface, this is valid for whom? Opaque surface. And for any surface in general, for any surface in general, what happens? Just now I told you that alpha plus rho plus tau, this is equal to 1. Clear? Okay, let us go to the next. Now the question arises that what is this relation for black body? So for black body, what happens is that this body absorbs all the thermal radiation. So this alpha b is equal to 1. Then rho and tau, this is automatically 0 only. Got the idea? Now, and for those bodies which reflects all the energy incidents, like I told you now, that there can be instances that a body is reflecting all of the energy incidents. So for body who are reflecting, for body reflecting all the incident radiations, what happens? Those bodies who are reflecting all the radiations, your rho value, that means your reflectivity, is equal to 1 only. Okay. So these properties again, these properties are defined for a surface, but these properties may again change with the wavelength. So please mind this word, that these properties like alpha, rho and tau can change with what? Can change with the wavelength of incident thermal radiation, can change with the wavelength of incident radiation, with the wavelength of incident radiation. Okay, next. Now let us understand one very good concept of thermal radiation. So let us now understand laws of thermal radiation. So laws of thermal radiation. So what is law of thermal radiation? First is Kirchhoff's law. So Kirchhoff's law of thermal radiation. So what I am going to write down here is Kirchhoff's law of thermal radiation. Kirchhoff's law of thermal radiation. So what happens in Kirchhoff's law of thermal radiation? This law states that whenever a body is in thermal equilibrium with its surrounding, like there can be instances or not instances, like most of the time bodies are in thermal equilibrium with their surroundings, then what happens is that whenever you are in thermal equilibrium, then your emissivity is equal to the absorptivity. So this is very important relation in order to understand the thermal radiation. So what I am trying to say is that whenever a body is, if a body is in thermal equilibrium, if a body is in thermal equilibrium, is in thermal equilibrium with whom, with its surrounding, with its surrounding, then I am writing in terms of symbols that its absorptivity will be equal to its emissivity. What does it mean? That whatever you are absorbing, you are emitting those, not reflecting. Reflection is a separate thing. Okay, so if I am emitting those who I am absorbing, then I am maintaining my thermal equilibrium, right? Let us say if I am 10 degrees Celsius and let us say that I am absorbing 100 units of radiation, then this 100 units of radiation has the capacity to change my temperature. But if I am trying to emit this another 100 units from my body, then what happens is that I am in thermal equilibrium, like whenever whatever I am absorbing, I am emitting them. Okay, so if my body is absorbing how much and emitting how much, if these two things are same, then I can say that my body is in thermal equilibrium always. Okay, great. Then let us now move to again whom Planck's law of thermal radiation. Next important topic is Planck's law of thermal radiation. Planck's law of thermal radiation. So we should just know what is this law as of now. There is nothing much to be worried about this law. Okay. So this law says that your monochromatic emissive power of a black body is dependent upon both the absolute temperature of the black body and also on the wavelength of the energy emitted by the body. So what I have said is that my black body emissive power, or more specifically I am talking about spectral emissive power or monochromatic emissive power. So what I am writing down here is that my monochromatic emissive power EB lambda, this is function of whom? This depends upon the wavelength of the body or wavelength of the energy body and also the absolute temperature of the body. So this is function of lambda and T. So what I have said is that your EB lambda is function of lambda and T. Okay. Then this is derived as EB lambda. Then what is that relationship I am writing down here? is 2 pi C1. This relation is not important for you to remember, but you should at least see that how this look like. Okay, into e to the power C2 upon lambda into T minus 1. Okay, so this is your EB lambda. Okay, so this is your EB lambda. So once you know these laws like Planck's law of thermal radiation, then if you integrate it between your given limits, then you can find out your emissive power. So the Planck's law of thermal radiations becomes what? Very basic of your other laws of thermal radiation. And one more important thing is that what is that we have seen some C1 and C2 here. Yeah, so this C1 and C2, what is this C1 and C2? These are experimental constants. C1 and C2 are experimental constant, experimental constants. Okay, let us go to the next. So the next law is Wiens displacement law. What is that? Wiens displacement law. Wiens displacement law. This is very important with respect to the PSU exams. Wiens displacement law. So here when you go on finding out like your like Planck's law we have seen now, so when you try to draw it graphically, then what was the observation we found? That your lambda m is inversely proportional to 1 upon T. Like what is this lambda m and T? See, whenever your absolute temperature of black body increases, EB lambda also increases, but most of the thermal radiation was shifting to the shorter wavelengths. Like if I help you to draw the graphical representation of displacement law, then what does it happen here is like you have EB lambda here. Okay, EB lambda, and here you have lambda, and corresponding to this lambda and EB lambda we are trying to draw a graph. So what is that? That your EB lambda value is increasing with the help of lambda, and then it is decreasing, and this I have drawn for whom? Here my temperature is constant. Okay, and then corresponding to this one we have one maximum lambda, right? Like lambda m is what? Like lambda m I have written here. So this is lambda m corresponding to what? I have the maximum emissive power. Okay, so this is for constant temperature. Then again if I try to draw another constant temperature lines, then the shift is something like this. Then can you see that when my temperature has got changed, and then my lambda m has also got changed, and this is again, let us say this is T1 and this is T2, then what is this T1 and T2 in this curve? T1 is greater than T2. So can you see here that when your T2 value like when your temperature has got decreased, then your lambda m has increased? Yes or no? Like lambda m is increased. So can you see now that lambda m is inversely proportional to temperature? Yes or no? That here your lambda m value was lower, but your temperature value was higher. Here your lambda 1 m value is higher, but temperature is lower. So this observation is called Wiens displacement law. What is that? Your lambda m means what? That this is the lambda corresponding to which I have the maximum power. temperature, like at what temperature you are talking about, this remains constant. This is what Wiens displacement law says, that this product is constant, lambda m into T, and for calculation purpose this lambda m multiplied by T is approximated to 2900. Okay, now so lambda m into T is constant, and this value is lying somewhere around home 2900. Okay, now next is Stephen Boltzmann's law. So Stephen Boltzmann's law we have seen earlier. What it says, that your EB value, emissive power, was directly proportional to whom? Fourth power of absolute temperature. Then your EB value is also equal to sigma T to the power 4, and this sigma is nothing but Stephen Boltzmann's constant. What is this sigma? Is Stephen Boltzmann's constant. Okay. So this is sigma, and what was this value? This was equal to 5.67 into 10 to the power minus 8 watt per meter square into Kelvin to the power 4. So this is known to us. And then what is the emissive power for non-black body? Like this you have written for black body. So for non-black body we have seen that when we multiply it with the emissivity, then if I am willing to write down what is E, then can I write down this is nothing but E epsilon into emissive power of the black body. Then can I write down this is epsilon sigma T to the power 4. Yes, I can, no problem at all. Okay, so this is the case, right? So what I can say now is that my Planck's law has given us two things. One is Wiens displacement law, and another is Stephen Boltzmann's law. Okay, so sometimes they ask us that which of the following helped us to reach other laws, or they can ask you that Wiens displacement law is derived from, Stephen Boltzmann's law is derived from. So we should take care that these came from Planck's law only. Okay, and then if somebody sometimes asks you that what is the unit, here the unit is watt per meter square, and then if they are willing to ask me that what is the E into EB in watts, then can you write down this is E sigma T to the power 4 into multiplied by area, then can I write down this is nothing but watts W. Okay, next, Planck's law we have seen. Now let us go to whom? Let us go to Lambert's cosine law. So this is Lambert's cosine law. So what this law says you, that intensity of radiation I you have, and along any specific direction is defined as the radiation energy emitted from the surface per unit time, per unit area, and per unit solid angle about that direction. So what is this is something like this. See, so let us say that there is a body, and then yeah, So if there is a body, then this body has the capacity to emit radiation I along any specific direction, right? So what is this I? This I is nothing but dE upon what? dW. So this is nothing but solid angle. Okay, so how can I write? What was the dE? This was nothing but watt per meter square. And now if I am defining I as the intensity of radiation, what is I here? I is the intensity of radiation. I is intensity of radiation. So I intensity of radiation is d per dE upon dW. This is energy emitted per unit time, per unit second. This I know, right? And now I am defining that what is per unit solid angle. So the unit is Stardian. Okay. So now I know what is intensity of the radiation. Okay, now what is that I, if I know, like for any direction I know. Now if I say that, let us say that this is a surface, then if I have this I and this is my IN, then if this is my theta, then what I am trying to say you is that you know about it any given direction, then I am trying to find out what is the intensity of normal intensity of the radiation. Like intensity of radiation I know, then I am willing to find out what is the normal intensity of radiation IN. So IN is normal intensity of radiation. Normal intensity of radiation. Okay, so this is IN. So now I can write I is equal to nothing but IN multiplied by cos theta. So this is called Lambert's cosine law, that I is equal to IN cos theta. Okay. Now, so now if you are willing to find out what is the emissive power, so can I see that emissive power, like one relation we have seen that I was equal to dE upon dW, right? So can I write down that dE, if you integrate, then this is nothing but like energy only, right? And then if you integrate it between 0 to whom, pi, this intensity of like this limit of solid angle is like this can start from this one and then reach till what point, this one again, then what is the limit? 180 degree, right? So what I can do is that I can integrate it between 0 to pi I into dw. Okay, so this is the again one relationship to help you find out what is your intensity of radiation, and this is the unit watt per meter square. I hope you got it. Okay, so for black body, like for black body, what happens again, that black body is a diffuse surface. Like for any diffuse surface, not even black body, for any diffuse surface, I is independent of direction, we have seen, right? So for diffuse body, for diffuse body, what happens that I is independent of what? Of direction. I is independent of direction. Then then I can say that I is uniform in all the direction, then its dependency upon solid angle is nothing much, right? So I can only write down this is I is constant, right? So now I can write down that E for that cases, for diffuse cases, so what I can write, that I into nothing but pi. Can I write? Yeah. So for black body, how can I write down? For black body, for black body is also a diffuse body. So for black body, what is this? E is nothing but EB. Then can I write down this is pi into IN? I'm writing IN because what? That I is equal to IN cos theta. Yeah, and moreover, this I is to remain constant. So if I is to remain constant, then I is equal to nothing but IN. Then that is why I am writing that EB is equal to pi into IN, the intensity in the normal direction. Okay. Okay. Now see, let us understand, whenever you are exchanging heat with the radiation, then what happens is that, like let us say there are two bodies. Let me draw two bodies first. Let us say there is one body here and there is another body who is lying here. Okay. So what happens is that, like now I am willing to find out, like till now you know what is your emissive power, but you don't know how much heat you can exchange with the another body. So this is a safe factor who will help you to understand that what is the net heat exchange. What is that? Like let us say that this is body 1 and this is body 2. Then this body is also emitting radiation, like let me draw the blue one. Then this body is emitting radiations, right? and 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 this lower body, body 2, is also emitting radiations. Yes, so this body is also emitting radiation. So what happens during the exchange, that there is someone started travel from this point and will reach till this point. Okay, like will reach surface 1. Similarly, there will be some radiations emitted from surface 1 and they will reach to surface 2. Okay, they will reach to surface 2. So these are the instances that there can be travel starting from this point, they can reach this one, and then travel can start from this one and they can reach this one. Okay, so can you see that we need to define that what is that fraction which will be leaving 2 and will be reaching 1. Similarly, what is that fraction of emitted radiation which will start it travel from the 1 and will reach 2. So this is nothing but safe factor which helps you to identify. So what we are going to study next is safe factor. Okay, we know what is this like now before like going to safe factor, we know what was the basic concept behind safe factor. Okay, so now let me help you to understand it. Okay, so let me draw that bodies again. Like let us say that there's body 1 and there is another body 2. Then let us say that this body is emitting 100 units, and out of these 100 units, let me say that 60 units has fallen from, like started from 1 and reached 2. Why? Because there can be instances that some of the radiations who has traveled from 1 but not reached to 2. Okay, and there can be again instances that when you are at surface 2 and let us say that surface 2 is also emitting some energy, and let us say that surface 2 is emitting, let us say, for 50 units. Okay, and then from this 50 units, how much is reaching this one? Let us say that only 30 units is reaching this one. Then Okay, so now what I can see is that F12 and F21 accidentally here became 1, like, but this is not the case every time your F12 will become F21. It might happen that this is not the same. Okay, so you need not to mug up that these two will be same. Okay, there are instances when these two are same, but this is not exactly that every time they will be same. Okay, so now I understand safe factor. So safe factor I have denoted like by some denotion. So what you can see is that it is the fraction of radiation energy leaving a particular surface and then it is reaching the surface too. Okay, so in standard notation, like let us say that if I say Fmn, then what do I mean? That fraction of energy, fraction of energy, or specifically what is here, radiation energy. So fraction of radiation energy leaving surface 1, leaving surface 1, surface 1 and reaching surface 2. Okay, and reaching surface 2. Next. Okay, so what is the possible value of safe factor? So what is the possible value of safe factor? The possible value of safe factors are what? Like it can start from 0, like there can be instances that none of them is attracting, and then Fmn is lying between whom, 0 to 1. It can happen that all of the incident radiations emitting like all of the radiations leaving surface 1 is reaching surface 2. There can be instances that this is possible. Okay, and every time F12 will not be equal to F21. It might happen that any one of these is more or less. Okay, so let us see through few examples of the safe factor. Let us say there is a and there is one more case is that we will study here, that there can be instances that there can be FMM. What does it mean? That fraction of energy, energy leaving surface 1, leaving surface M, and reaching the surface M itself. Reaching the surface M itself. There can be instances. Okay, so what is, like let us say that I am talking about surface 1. So what do I denote it as? F11. Maybe like I am talking about surface 2. So how I can denote it? F22, right? So now let us understand it through some examples. Let us say that there is a flat surface. There is a flat surface. Then what is this? Flat surface. Then my idea is to find out surface flat surface. If this is surface 1, then what I am trying to say you is that if this surface is emitting radiations, if this surface is emitting radiations, then what are the chances that the same radiation will attract this surface again? Then chances are nil. Why? Because there is no chance that this will come back to this surface again. Okay, so what is F11 here? F11 in this case is 0. Again, let us draw another example. Let us say that I am trying to draw concave surface. Concave surface. Then what happens in this concave surface? Let us say that this is the concave surface. Okay. Then if this surface is emitting radiations, then can you see that there can be instances that these radiations will travel to this surface again? Yes or no? If I say that this is surface 1 again, then can you see that there can be instances like this can hit this one again, this can also hit this one again. then can I say here is that my f11 is not equal to 0, rather it is greater than 1. Yeah. So this is the example of what, like there can be instances when your energy is leaving that surface and reaching the surface again. Okay, then let us try to understand with another example. Let us say that you have convex surface. Okay, and if we have convex surface, then what happens here is that, like let us say this is the convex surface. Okay, and this convex surface is emitting radiation. So can you see that none of the radiations will travel back to this surface again, like it cannot reach its surface. Then again, what is the case? My f11 is equal to 0 if I name this surface as surface 1. Okay, let us do few more examples. Now let us say that there is a circular plate. Okay, and there is a hemispherical plate above it. Okay, this can happen, that there is a circular plate and there is a hemispherical plate above it. I name it as surface 1 and I name it as surface 2. Then one is circular plate and 2 is hemispherical plate. Okay, then again what I am trying to find out is that what is f12, what is f12. So f12, can you see, f12 is nothing but the fraction of energy leaving this surface. Then this surface has nothing but the only option that all of the radiation emitted from this surface will be directly hitting the surface 2 again. So f12 in this case, like radiations emitting from surface 1 reaching surface 2, the chances is what, that all of them will reach this one. And now what is f21, f21. Now, like just now we have seen what kind of surface is this one, this is convex surface. So from this surface, like, but now what is the surface who is emitting radiations? So this is nothing but these are the interior surfaces which are emitting radiations. Okay, so interior surfaces, if they are emitting radiations, like let us say that if I talk about this point, then what happens is that this is emitting radiations in these directions. Then what happens is that there are chances that f from something leaving surface 2 will reach again surface 2. So what I can see is that f22 is greater than 0. Yeah, so if f22 is greater than 0, then all of them will not reach 1, rather someone will reach 2. Then can I say that f22 value is less than 1? Sorry, f21 is less than 1. Got the idea? And f22 is than 0 and its value will obviously be less than 1. Yeah, so I hope that you understand what is the concept of f11, f22 and how to retrieve. Of all shape factors, one is reciprocity relation between shape factors. So what I am trying to write down here is that reciprocity relation between shape factors. So what is this relation? Reciprocity relation, this theorem says that, like if there is a body 1 and there is a body 2, okay, and if these two bodies are interchanging heat with each other, then if this one has area A1 and this one has area 2, then if this is f12 and this is f21, right? So what is the chance that A1 f12 and we have f12 A2 F21, like A2 A1 is having what surface with safe factor F12, and similarly A2 has F21 with respect to each other. Then this relation says that this value A1 F12 will be equal to whom? A2 F21. A1 F12 will be equal to A2 F21. This is the case. Okay. Now if there is a, let us say, chemical base, or let us understand one more theorem here only, then we will be able to solve the few problems based on this, and that is called summation rule among safe factors. So what is that? Summation rule. Summation rule among safe factors. Summation rule among safe factors. So what is this summation rule? This summation rule says that if I have, again, like there is a body and it is like, let us say there is a body one. For example, let us say here only, like there is body one, and in case of there is only one body, let us say that there are n number bodies surrounding it. Okay, then what happens is that this body can interchange what? Its energy with, right? What your summation rule says that your F11 plus F12 means summation all factor equal to what? And this is true now. Then what is the unique into this? There is but okay, this is there, then this is okay. But can you see what is the sum of these two? And what is this trying to help you know is that, let us say that my 60% has reached this one. Let us say that 0.5%, 0.05 has reached this one. 0.1% has reached this one. 0.2% has reached this one. Let us say again 0.05 has reached this one. Then what is this? That 0.2% again reached this one. Then can you see that, let us say this is 0.1, then can you see that this is the nothing but the safe factor, like 0.05, 0.1, 0.2, 0.05. These are nothing but the safe factors only. Then the sum of all these safe factors will be equal to 1. Yes or no? Yes only. Why? Because if I have emitted 100 radiations, then it must be reaching these surfaces, and the sum of that fractions will be always equal to whom? Will be equal to 1. So this is what summation rule is helping you to know. Okay, so let us now questions based on this. We will move forward. Let us say that there is again we have seen this example now, like let us say that there is a circular base and one hemisphere is enclosing it. Okay, so now this is surface 1, this is surface 2, and if I dash like this one, then what does it mean? That it is emitting radiations from this surface. Okay, so this is surface 2, this is surface 1. Just now we have seen that F12 value is equal to 1. Okay, and what is F21 now? F21 is not known. So we have seen this relation now, that A1 F12 is A2 F21 from reciprocity relation. And what is A1? Like let us say that we will denote in terms of R. Then what is A1? A1 is nothing but pi R square. Okay, and F12 we have seen is 1. So pi R square into 1 is equal to A2 value. A2 value is the surface area of this one, and the surface area of hemisphere is what? 2 pi R square. 2 pi R square multiplied by whom? F21. So here, from here, what you can see, what is F21? That this R square and this pi, this R square and this pi is got cancelled out. So F21 value is 1 by 2. So can you see, just by using reciprocity relation, we are able to find out what is the various safe factors we can see, right? And then they can ask you what is F22. What is F22? So we will use which theorem to find out F22? The summation theorem just now we have seen. So what was that? That F11 plus not f11, f12 plus or let us say f21, like we are trying to find out f22 now. So that is why how I will write that f21 plus f22, this will be equal to 1. Okay, so what is f22? F22 is equal to 1 minus f21. This is equal to 1 minus f21 value is 1 by 2. This is 0.5. So can I see that f22 value is 1 minus 0.5. This is equal to 0.5 only. Yeah. So f22 value is 0.5. Okay. Now let us solve one problem based on this problem, like on rule of summation itself. So let us say that how I can help you understand. Let us say that there are three surfaces. Okay, one surface is this one, and then there is another surface here is this one. Okay, then they are willing to ask us that, like, let us say this is surface 1, this is surface 3, and this is surface 2. Okay, 1, 2 and 3, and this is the length of this surface, and this is the diameter. Okay, and it also says that length is equal to diameter. So now my job is to find out what is f22. So can you see that what is f11? Reach started from 1 and reaching 1, so this is nothing but 0. So f11 is directly 0. Now what is f12? F12 is what? So what I will do in order to find out f12, that f21, how you will find out f12 and f13. So let us say that f11 is equal to 0, f12 we need to find out, and f13 we need to find out that what is f1 and 3. So let us try to apply the reciprocity theorem. So can I see that A1 F12, A1 F12, A1 F12 is A2 F21. Yeah, and now I don't even know what is F21, but I know one thing. What is that? That F21 from the symmetry I can see that F21 will be equal to F23. F21 will be equal to F23. Okay. Now, and I also know that f21 plus f22 plus f23 will be equal to whom? 1. So using these relations we will be able to find out what is f21. So you have been given one thing is mentioned to us in this problem, is that f13 is given to us. If they don't mention any one of these, then it will be very difficult for us to evaluate. So f13 is given to us, and this value is given to us as 0.17. So now first let us first determine what is f12. So f12 is determined by whom? The summation theorem. So can I write down f11 plus f12 plus f13 is equal to what? 1. f11 I know this is 0, f12 I need to find out, and f13 I need to find out using this relation. So this was already given, right? This is equal to 1. So can I see that f12 is 0.83, that is 1 minus 0.7. So f12 is done. Okay, so f12 is done. If f12 is done, then this I know, a1 I know, and a2 I also know. Then I can find out f21. So when you will solve for this f21, then what you will get is that f21 is equal to what? a1 by a2 into f12. So a1 by a2 into f12, and f12 value is what? 0.83. And what is a1? a1 is pi by 4 d square. And what is a2? A2 is nothing but the surface area of this one. This is nothing but pi d multiplied by this distance, which is L, but here it is given as what? Equal to diameter pi dd. So pi d square got cancelled out. This is 0.83 by 4. So now I know what is F12. I also know what is F21, and then coming to this theorem, then I know what is F21, right? I don't know what is F23, but using the symmetricity theorem, like F21, like if two surfaces are kept at equal distances, then I can say that their summation, like their view factors will be sum. So F21 will be F23. So F21 I know, then I know F23 also. Then what is F22? F22 is 1 minus F21, or I can say that twice of F21, and this is equal to 1 minus F21 value is 0.83 by 4. So 0.83 by 4 into 2. So this is 2. So this is nothing but 2 minus 0.83 by 2. So when you will solve this one, this will turn out as 0.585. Okay. Now let us quickly move to circuits. So whenever you are having like radiation exchange, then we should know what is the radiation resistance, right? So let us now understand radiation networks. Like we have seen conduction network, right? So let us now understand radiation network. So first thing is irradiation. First thing is irradiation. So what is this irradiation? It is the total thermal radiation incident upon a body, denoted by whom? J, G. So what is this G? Is nothing but whatever the thermal radiation energy incident. So thermal radiation energy incident. Okay, so this is what called irradiation, and then we have next thing as radiosity. Radiosity denoted by whom? J. So what is radiosity? It is the total radiation energy leaving the surface per unit time and per unit area. So denoted by whom? J. So this is the radiation energy which is leaving the surface per unit time, per unit area. So what will be this J value? J will be considering two parts. One is that one which you have emitted, right? So one is that one which you have emitted, plus second is that one which you have reflected, right? Emitted plus reflected. What is emitted? Emitted is nothing but E into EB, and what is reflected? Rho times of what was falling upon you, G. Can I write like this one? And I can also write for any surface, like for opaque surface, if I talk about, like it is, if it is not transmitting, then can I write down that alpha plus rho is equal to whom? 1. And for thermal equilibrium I know alpha is E, then can I write down rho is equal to 1 minus E? So this is nothing but now E into EB plus this is rho is 1 minus E into G. Yeah, so now I know J is the total radiation, what this is, which is leaving me, right? So radiation energy leaving, radiation energy leaving the surface, leaving the surface. Okay, now then I know G and I know J. So the net will be what? The difference of these two, J minus G. So the difference between J minus G, the difference between J minus G, then if I can write Q net, that what is the net effect with the surface and the surrounding. So Q net will be what? The difference of J minus G multiplied by whatever the area you have. What? Yeah. So this is one. So now if you expand this one, then you know that J minus G would look like that J was just now we have derived that this was E into EB plus 1 minus E into multiplied by whom? G minus of G into multiplied by whom? A. Okay. So now Q net I can write, if I wish to write down Q net, then Q net is nothing but, can I write down the with the surface and the surrounding, this is nothing but EB minus J divided by 1 minus E upon A. Okay. So this is now your whole effect of whom? Your, like you are trying to see, this is nothing but I am replacing this G with respect to J. So can I replace this J with whom? J. G I can replace with J. See, I am telling you that this G I can replace with whom? J, by using this relation. And then when you will replace this one now, then your Q net would look like something like this. So see, now my Q net is telling me what? That the black body emissive power minus of J means what you were trying to leave is nothing but the net heat exchange divided by whom? Your net, what? Your surface resistance. So now can you see that this resistance has come into picture, and this is what, that if this was my black body emissive power, and this was what? This was the total energy which was leaving me, then the difference between these two is the net effect with the surrounding, and then what is the resistance which is helping me to hinder it? This is 1 minus E upon AE. So this is defined by whom? This is the surface resistance. Okay. Okay. Then let us move to the next. Then surface resistance concept I know. Then again let us go to that two surfaces exchanges energy. Then can you see that that again what will be the fraction reaching from surface 1 to surface 2? If I am leaving J1, then J1, like let us say that this is surface 1, this is surface 2, then I am willing to find out that what is the amount now. Like till now you know what is the fraction, but now I am willing to find out the amount. Then what you would do is that you will simply, like from this one you have energy leaving this one and reaching this one, then what was that fraction? F21 I know, and the area I know, that what is the leaving one? This one A1, and then if I multiplied by whom? J1, then I know that this is the F21 into not this is leaving surface 2, no? So A2 and J2. So what this is the amount of heat exchange by whom? From 2 to 1. Got the idea? Similarly, what is the amount of heat exchange between 1 to 2? So what is that? From 1, like this is the amount, like this is the amount I am telling you is started from and similarly from 1 to 2, what will be that amount? F12 multiplied by area A1 multiplied by what is its radiosity. So again, what is the net? What is the net effect? Net effect is again the difference between these two. So can I write down net effect is nothing but F, like whoever is dominating will decide. So let me write down for any random like 1 to 2. So 1 to 2, what is that? Like J1 A1 F12, J1 A1 F12 minus J2 A2 F21. Why I am writing like this is that, like this is the amount A1 F12, J1 A1 F12 is leaving, and J2 A2 F21 is coming on to it. So the difference between these two is nothing but the net effect. Okay, so now what is my Q net? What is my Q net? Again, can you see that this was nothing but J1 minus J2, J1 minus J2 into, if I wish to write, I can write like this one, and if I wish to write, I can write like this one. One thing which must have hit your mind now is that I can write this one y F12 was A2 F21, and what was the earlier difference? You can see from this slide that here I have A1 F12, here I have A2 F21, and I know from the reciprocity theorem that A1 F12 is equal to A2 F21. Then I can write Q net is equal to J1 minus J2 into A2 F12. So now can I write down that Q net is equal to J1 minus J2 divided by 1 upon A2 F2 A2, if in terms of, like I am writing in terms of 1, then can I write down that this is A1 F12? Yeah. I understand that this is again one of the ways to write down the Q net. Then can you see that again this is nothing but the resistance. Now this is what kind of resistance? Space resistance. Yeah. So now any thermal circuit will be, any radiation thermal circuit will be considering what? Like let us say you have surface 1, you have surface, let us say surface 2. Then between these surfaces, what do we have? That if this is surface 1, emissivity E1, then here what do we have? Surface resistance as 1 minus E, 1 upon A1 E1, and here we have space resistance. This is just now we have seen that this is A1 F12 or A2 F21, both of the values are same. And if this is surface 2 and emissivity 2, then this is 1 minus E2 upon A2 into E2. So now what do we have is that we have EB1. One thing we do have is EB1, and then we have surface resistance 1 minus E upon 1 minus E1 upon A1 E1. Okay, and then we have space resistance, this is 1 upon A1 F12. Yeah, and then again we have what? Surface resistance, what is this? This is 1 minus E2 upon A2 E2, and now here what do we have? EB1, and this is EB2, then this is J2, and this is J1. So can you see that between EB1 and J1, like between the surfaces, between the space, and again between the surfaces, right? So now I know how to draw the thermal circuits even, and if I know to draw the thermal circuits, then I can solve this problem like any given problem by just applying the thermal circuit concept. Okay, so can you see now that I can write down that Q net, and I am telling you what, that the radiation, net radiation heat exchange. So can I write down this one like that? This is nothing but summation of thermal resistance, which are nothing but radiation resistances also. So now I know that how to apply electrical analogy given to the radiation problems also. Okay, now let us quickly apply to few cases. Let us say that there are two infinite parallel surfaces which are exchanging energy with each other, and then these are denoted like, let us say this is surface 1 and this is surface 2. Then if you draw thermal circuit, and how it would look like is this one only. And if this is, let us say that this is EB1, this is EB2, then what is this? This is 1 minus E1 upon A1 E1, this is 1 upon A1 F12, and this is 1 minus E2 upon E2 E2. Okay, so this is E1 E1, this is E2, this is A2. But I am applying for simpler cases that A1 is equal to A2, like these are two infinite parallel plates, then the areas are same. Okay, so the F12 value is equal to F21 here. Okay, and this 2 is nothing but 1 only. Why? Because these are infinitely parallel. So now if you go on writing that what is the q net, then how you will write down? This is nothing but eb1 minus eb2, so I am skipping that part. I am directly writing the values of eb1 and eb2. So can I write down? This is nothing but sigma t1 to the power 4 minus t2 to the power 4 divided by, now let us write down this one by one. So can I write down? This is nothing but, if A I am taking on the upper side. Okay, so in fact I am taking A as the unit area. Let us say that A1 is equal to A2 is equal to 1 meter square. Then can I write down? This is nothing but 1 minus E1 upon E1, 1 minus E1 upon E1. This is 1 only. Why? Because area is 1, F12 is 1, so this is 1 only, and this is 1 minus E2 upon E2. Yeah, so then when you will solve this one, then what you will reduce is that sigma t1 to the power 4 minus t2 to the power 4 divided by 1 upon E1 plus 1 upon E2 minus 1. So can you see that if you are able to apply the equivalent thermal circuit problem, then you can always solve the problem within the seconds. So now I know what is the thermal exchange between these two plates. Otherwise what you will have to do is that you will have to calculate all of them individually, which is never the good case. Okay, now let us apply this to radiation shield problem. So now let us apply it to radiation shields problem. So what is radiation shields? There are certain scenarios where you are not willing to lose the heat between two surfaces, more specifically in case of furnaces. So what you are trying to do is that you are trying to introduce one radiation shield which is obstructing the heat exchange between, let us say, surface 1 and surface 2. Okay, so if this is at, let us say, T1, its emissivity is E1 and this is E2 and the temperature is T2, then I am introducing one what shield here. So what is the job of this shield? Let us see what this shield will be able to do. So now if I draw the thermal circuit, then what is that I have one surface resistance here, one space resistance between these two, or let me draw with the help of given space only. So there is one space resistance. When you reach this surface, you have one what again surface resistance on this side, and again one surface resistance on this side, and there is one surface resistance space resistance again, and then again you have surface resistance. Okay, so can you see one radiation shield has introduced so many changes? Earlier what do you had? Earlier you had this resistance and one space only, right? But here what do you have is that you have, like earlier you had three resistances. Let us say that this was the one space. Okay, but now you have what, two space resistance, like one space resistance which has been added, one space resistance plus two surface resistance. So you see that one radiation shield, these are introduced by one single what shield. So introduced by one single shield. Okay, so let us say that if you are introducing n shields, then how many surface resistance it will introduce? 2n. And how many space resistance? N. So got the idea? There can be questions based on this fact also. Okay. So how much energy you are able to reduce, like how much energy, so you will have to take care of all these. But let me help you to draw with one special case. Let us say that emissivity of all the surface, E of all the surfaces are same. Like when E of all the surfaces are same and your area is also unity, like you are trying to find out, like I am not telling you unity, this is area is also same, then you are trying to find out in terms of per units. In terms of per units, then what would happen is that if I go to write down q value, then this q value looks like what, like this will be sigma again t1 to the power 4 minus t2 to the power 4, and you will introduce all the resistances here. Then what it becomes like that, earlier like for E is equal to bodies, then what it happens, like if I write down q without shield, q without shield, then this is nothing but sigma t1 to the power 4 minus t2 to the power 4, and here we had 1 upon e1 plus 1 upon e2 minus 1, and e, if the e are same, then what is become that 1 upon e1 plus 1 upon e2 is nothing but 2 upon e. Why? Because e1 is equal to e2, and this is 2 upon e, this is watt per meter square. Now let us go for whom, q with the shield, then this is to the power 4 minus t2 to the power 4 divided by, this becomes what, 2 times like if I go on writing the resistances, then this becomes 4 upon E minus 2. Okay, and if you take 2 as the common one, then this becomes what, sigma t1 to the power 4 minus t2 to the power 4 divided by, what do I write, is that 2 upon E minus 1 was the earlier case, and then if I multiply it by 2, then this is the case. Then if I take that 1 by 2 as the common, then this is nothing but q width. Yes or no? Q width is nothing but this one, and this is nothing but here also q with without. Q without is this fact, right? So I can write down that q with the unsealed, q with one sealed is equal to half of q without. Okay, when your emissivity is same. So can I generalize it? Can I generalize it? And how do I generalize it? How do I generalize it? How do I generalize it? Is that QA means per unit area 1 to 2 net with unsealed seals will be equal to 1 upon n plus 1 multiplied by q by a, whom with seals. Okay, so this is the all about radiation. So we should just practice that, how to write the thermal circuit, how to put the values of E1, E2 and other things, then you will be able to solve the questions. Okay, so this is all about like thermal radiation. So in the next class we will solve few problems based on the radiation, and then we will study about the convection also, and probably will be able to finish this topic. Okay, so thank you very much. Okay, so we'll end this class and we will study tomorrow.